Okay, Bismillah ar-Rahman ar-Rahim. Inshallah Rabbil Alameen, using this video, inshallah, we will talk about a very important and essential phenomenon in generating electricity, which is called electromagnetic induction, which is called a what? Electromagnetic induction. Okay? If you remember, we said we have three inductions in electricity and magnetism. The first one is the magnetic induction. And magnetic induction happens when magnetic material is placed in an external field of an external magnetic field, like the field of inside a solenoid with the current carrying wire, with the direct current carrying wire, DC, okay, and electrostatic induction, and we said this is removed from our syllabus, okay, in the most recent version. Number three, electromagnetic induction. Okay, so you have to differentiate between the three terms. Electrostatic induction, this is removed from our syllabus. Magnetic induction, which gives the induced magnetism. Okay, electromagnetic induction, which is this one. What is the idea of electromagnetic induction? This idea or this phenomenon was discovered by Michael Faraday. Okay, and it was very, 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 very important event in the history of physics. Why? Because Michael Faraday discovered that if we make any change, any movement, any relative movement between a magnetic field and a conductor connected to a circuit, there will be current flowing in the circuit without a source, again. If you have a number one, magnetic field, number two, conductor, either wire or coil placed inside this magnetic field. So we have magnetic field, number one, which is the region between two magnets, between the N pole of a magnet and the S pole of another magnet, or the N pole of and S pole of a U-shaped magnet or horseshoe magnet or anything like that. Okay, this is the region is called magnetic field. Okay, number two, a conductor. Number one, magnetic field. Number two, conductor. Conductor, wire, coil, solenoid, any kind of conductors. But in one condition, this conductor must be connected to a closed circuit without a source. Without a source. يعني ما فيش, there is no battery or no cells or something like that. No source of electricity connected to the closed path of this current. So we cannot say it's complete circuit. It's a closed path of current. If this conductor is connected to a closed path of current, okay, till now, what will happen? Can we get electricity? No, we never get electricity unless relative change happens. Relative change. What's meant by relative change? Relative change happens means the wire moves with respect to the field, or the field moves with respect to the wire, okay? Or the field changes, increases, decreases, opposes in direction, flipped its direction, okay? Any change like this will cause what? Will cause electric current to pass in the conductor without a source. Without a source. Okay? And be careful. This current will stay flowing as long as the relative change happening. Once the relative change stops, يعني مثلا the wire stops moving, or the coil stops moving, or the or the intensity or the field stops moving, or the intensity stops increasing or stops decreasing. Okay, if no change happen, the wire will cut off again. The wire will cut off again. This phenomenon is called electromagnetic induction, and it was discovered by Michael Faraday. طيب, let's ask ourselves a question. How can we know if this current flow? Someone may say, Mr. Put an ammeter. The ammeter is the device that we use to detect the current. It may be correct in other situations, but in this situation, we will not use ammeter. We will use another device which is called galvanometer. Or in other words, zero-centered galvanometer. What's meant by zero-centered galvanometer? The galvanometer is a device that measures or detects the very weak currents. This is the advantage of galvanometer with respect to the ammeter. The ammeter measures in amperes, okay, but the galvanometer measures in microamperes, okay? So it detects what? Detects weak, very weak currents, because it's expected the current to be weak if we make such an experiment. Such experiment in the laboratory. Okay, so detects weak currents. Not only detects weak currents, but it shows us the direction or the current direction. The direction changes of current. يعني because in this experiment, we have to look at a very important point. Mr. You said it's a relative motion that causes the current, relative motion that causes the current. I didn't say that directly because I'll add a very important point here. لكن, okay, Mr. If the current, for example, if this is a magnetic field here, I show all this on a video, but I give the theoretical introduction, okay? Now, this is a magnetic field. This is a wire. This wire is moving like this in the field. When it cuts the magnetic field lines in this direction, what will happen? It will produce current. Well, will the current be the same as if the wire going up? We will check this using a galvanometer. So we will use a galvanometer whose scale is like this: 0, 1, 2, and so on, 1, 2, and so on, okay? The pointer is here. When the current passes in certain direction, it will go to right. When the current opposes its direction, it will go to left. This is the galvanometer, the zero-centered galvanometer, okay? But the the ammeter, by the way, has the zero to the left. This is the ammeter, okay? So this is the galvanometer, and this is the ammeter. You get the idea? Okay. طيب, there is a very important point remaining. After that, we will see the video together, inshallah Rabbil Alameen. What is that important? First of all, if you are understanding what I'm saying now, and if you are still focusing on my words, please write 7. Yeah. You have any problem?
يس يا مس، انا سرحت الحته اللي فاتت دي،
اللي هي بتاعت ايه؟
اللي هو من دقيقه يعني.
يعني وصلت معايا لغايه اللي انا رسمه دلوقتي دوت، ان الجلفانوميتر عنده زيرو في النص دي وكده، ولا لا؟ ولا ده
اه
فات منك؟ طيب، يعني the zero center scale of the galvanometer, why is used to give me additional ability to see if the current changes its direction. Because if I reverse the direction of motion of the wire, for example, the current will reverse. And we detect that using the galvanometer. Till now, is it clear or not?
ايوه تمام يا مس.
تمام. Okay. Finally, what is the reason of this flow of current? Listen well. There is a very important point you have to say whenever you talk about the current, the electromagnetic induction. Okay? When the conductor, and when I say conductor, I mean one of two things: wire or coil. Here, coil, this coil may be solenoid, but it's not practical. Okay? Rectangular coil, and so on. When conductor or a conductor cuts or move or when field moves, when magnetic field moves, or when magnetic field changes direction, changes its intensity or strength, أحسن, either increasing or decreasing when magnetic field changes its direction. If any one of these happen, memorize these situations: 1, 2, 3, 4. Okay. If any one of these happen, طبعا this is if a conductor is in a magnetic field. Please write this after me or take a screenshot. Okay, I'll send it to you, inshallah, I mean, after the class. Okay, if a conductor is in a magnetic field, this is number 1, and not parallel to it. يعني the conductor is not parallel to the magnetic field. Okay, if these two conditions happen together, so 1, 2, 3, 4 events will cause what? Will cause conductor to cut magnetic field lines. When the conductor moves, or the magnetic field moves, or any change happens, this will cause the conductor to cut the magnetic field line. It doesn't mean cut the magnetic field line, and the magnetic field line will be cut and do like this. لا. It means it will pass through the magnetic field lines. Okay. If this happens when the conductor cuts the magnetic field lines, what will happen? What will happen? This will cause the free electrons flow in the conductor. The free electrons flow in the conductor, okay, causing something called, causing potential difference, which is called induced, causing potential difference. Why? Because when the electrons flow, they will accumulate in one side, okay, leaving the positive in the other side. So now we have positive and negative. So potential difference will be formed inside the conductor, which gives something called induced electromotive force. Induced electromotive force. This is the idea of electromagnetic induction. And now let's see the طبعا you have to memorize this word, cutting magnetic field lines. If I ask you, why is there induce the electric current, your answer has to include or must include this point in your answer, because when blah 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 happens, conductor cuts magnetic field lines, so induced electromotive force is produced. You have to put this in mind. If you get what I said, please write 3. If you didn't, write 2. طيب الحمد لله. Now let's see the video together. Now this is the what? This is the what? Excellent
galvanometer.
answer. ايوه بالظبط كده. This is the galvanometer. It's zero-centered, as you see. The zero of the scale is in the center. Okay, and there is 10, 20, 30, 10, 20, 30 in the two in both sides. You here with me?
ايوه يا مستر.
ممتاز. This is a conductor, coil, solenoid. I said any conductor, so I write conductor. Okay. This is a magnet, so it produces a magnetic field. In this experiment, we will move the magnetic field around the conductor. So what will happen? What will happen? The magnetic field moves around the conductor. What will happen? There is a key word I told you to see. When it moves around the conductor will what? Excellent, mashallah. Thank you. Barakallah feek. It will cut magnetic fields lines. So induced electromagnetic force will be produced. يبقى it will do what؟ شكرا يحيى، شكرا مصطفى، شكرا أنس. It will do what يا يحيى؟ cut magnetic field lines. Okay, طيب. Let's see what will happen. بسم الله. This is the magnet. We will move it, yes, towards or inside the coil. If I ask you, where is the direction of deflection of the current? What is the direction of deflection of the current? Deflection, sorry, of the pointer of the galvanometer, I'm sorry. For the pointer of the galvanometer, it's to the right, okay? That shows the current flows in certain direction. And we don't know the specific direction of the current, but it flows in certain direction when the magnetic field lines or when the magnetic field moves in this direction. Okay, طيب. Let's see. Again, I won't stop here with a point. Look, as long as the magnet's moving, there is a current here in the galvanometer. Look, now the magnet is stopping. The magnet exists, and the current and the conductor is neighboring to the magnet. So they are in the same place together, okay? But there is no relative motion. So after bringing the magnet inside the coil, we stop moving the magnet. So what they see here, the galvanometer gives 0, which means there is no current. Why, Mr. طيب ما هو magnetic field inside the magnet is inside the coil. It's not the point to be inside the coil or outside the point. The point is, are they changing with respect to each other or not? If there is no change with respect to each other, if there are 1 million magnets and 1 million coils placed together in a space like this, nothing will happen. Nothing will happen. Okay? Well, let's continue. Now it's moving away. If you see, when it starts moving away, what happens? The deflection of galvanometer pointer is to left, okay? And so on. This is the electromagnetic induction, okay? Well, let's go to our notes. Well, so that's what we explained. So we will read fast and give some briefs or comments on what we are reading. Definition of electromagnetic induction: it's producing induced electromotive force in a conductor without an electric source when one of two things happen. When a conductor is moving across a magnetic field. Number two, when a changing magnetic field linking with the conductor. And when I say changing magnetic field, this may give the meaning of the magnetic field is moving with respect to the coil, the conductor. The magnetic field is increasing with respect to the conductor, even if it's not moving, or decreasing, okay, or changing its direction. any change happens to the magnetic field around the conductor or any movement happen to the conductor inside the magnetic field gives the electromagnetic induction. If it's clear, please write 5. قول يا أنس. If it's clear, write 5 please يا جماعة. ممتاز. Thank you. طيب, this is the experiment we explained. This is the symbol of the coil. This is the symbol of the galvanometer, and we have another symbol of galvanometer, by the way. This is the, it's in the list that I gave you. This is the magnet, and this is the experiment, as we explained, to avoid repeating this. Okay, conclusion is very important. Rate of a change in cutting, the induced current depends on, you have to put this in mind. The induced current will be larger when you make the change faster. And if you increase the rate of a change, the induced current will be larger. Okay, this is a very essential point. Okay, so if the rate of changing or cutting magnetic field lines is increasing, okay, or if the strength of the magnetic field is increasing, or if the number of turns of coil increases, if any of these change happen, this will give us larger intensity of the current. Again, يا جماعة, again, if I move the magnet, كله يركز please يا جماعة, if I move the magnet slowly inside the coil, or if I have this is another experiment. If I have a wire like this and I move it inside the magnetic field slowly, will the deflection of the current of zero-centered or center zero, okay, will the deflection be large or small? I'm waiting for your answers in the chat, please.
The deflection will be large or not?
يعني أنا دلوقتي بحرك الواير slowly هنا، أو في الإكسبيرمنت اللي شفناها بنحرك الماجنت slowly. تمام؟ هل يا ترى الكارنت هيبقى will the current be small or large؟ تمام؟ ها يا جماعة. Thank you. Small. Thank you, everyone. Why? Because the current is caused by the electromotive force, which is caused by the cutting of the magnetic field by the conductor. Okay, so as the rate of cutting magnetic field lines increases, the current increases. As it decreases, the current decreases. So, and put this in your mind, and this is one of the most important and the most frequently asked questions in the exam. If I ask you, why is the induced electromotive force, or why is the induced current increases without seeing anything, right? Because the rate of cutting magnetic field lines increases. طبعا you have to add additional details, لكن this will be إن شاء الله ربع مين part of your answer. تاني يا جماعة بيجي يسألني بقى يقول لي في الترانسفورمر في أي ديفايس في الدنيا ليه الكرنت هنا زاد؟ Why current increases? Why current decreases? This is because the rate of cutting magnetic field lines increases. لو جيت قلت لحضرتك ليه الالكتروموتيف force increases, one of the points of your answer must be because the rate of cutting magnetic field lines increases by the conductor increases. Why is it decreasing? Because the rate of cutting magnetic field lines by the conductor decreases. Why it became zero? Because the rate of cutting magnetic field line is zero. If you get this point, please write 1. If you don't, write 2. تمام الحمد لله. خلاص يبقى also if the strength of the magnet increases, what will happen? The electromotive force increases. If number of turns of the magnet of the coil increases, right? Rate, induced electromotive force increases, because all these changes will increase the rate of cutting magnetic field lines. Rate of cutting magnetic field lines by the conductor. Yeah. طيب. So factors affecting the size of induced electromotive force may be one of four things. Number one, speed of motion. Okay, speed of motion. Speed of relative motion of magnetic field lines. As it increases, the rate of cutting magnetic field lines increases, so the electromotive force increases. The length of the wire inside the magnetic field, okay, is, if it increases, that means the rate of cutting magnetic field lines will increase, okay, so the electromotive force increases. The strength of the magnetic field line, if we have stronger magnetic field lines, a magnetic field, okay, that means the magnetic field lines are more, because the magnetic field lines will be more crowded, okay? So the rate of cutting magnetic field lines will be more also, okay? The number of turns, in case of coil, if we have a coil, if it's a coil, so we have turns, okay? All these are, يعني هنا, this is for a turn or wire. This is for a wire, okay? This is for, sorry, coil or wire. This is for a wire. This is coil and wire. This is for a wire. This is for both. This is for coil. لأن إحنا, we said that we have two probabilities, either wire in a magnetic field or coil in a magnetic field. Okay? خلاص؟ طبعا if we have a wire, we will talk about the length of the wire. If we have a coil, we will talk about the number of turns of the coil. Okay, so as number of turns of the coil increases, what will happen to the magnetic field, the electromotive force, the induced electromotive force? It will increases. It will increase because the rate of cutting magnetic field will increase. Well, the direction of the induced electric current. We have two probabilities. If we have, listen well, يا جماعة, this is a very important point and the new point, okay? And the very, very important point again, okay? We want to determine the direction, for example, here in this situation in front of us, okay? If we don't have this arrow, so we don't know where will the current flow. Will it flow in this direction or in this direction? Yani when I move this wire downward in the magnetic field, okay, where will the direction flow? Will it flow inside the paper like this or outside the paper like this? I know it's written here, it's drawn here, but imagine that this arrow was not here, okay? How to know the direction of the current? In fact, do you remember the Fleming's left-hand rule? Do you remember the Fleming's left-hand rule? Okay, I think you remembered it because it's very important and we make, mashallah, يعني a large amount of practice on it. Okay, طيب. But Fleming's left hand rule, we used it to determine what يا جماعة؟ To determine the direction of what?
Force.
Force. Determine the direction of magnetic force or thrust or motion. Do you remember? We said that the force may cause motion. Okay, so we were saying magnetic force or magnetic thrust, okay, or motion. Okay, so but here we want to find the current. So listen well, we will use the same distribution of the fingers of left hand rule, but of Fleming, but to the right hand, to the right hand, or on the right hand. Okay, so we will apply the same configuration, the same distribution of the Fleming's left-hand rule, but we will use it with the right hand to get the direction of induced current. Okay, so if we have a straight wire moves perpendicular to the magnetic field, relative directions of force, field, and induced current is studied by a rule called Fleming's right-hand rule. And I think it may be relatively helpful if you make some kind of interference to remember that this is induced current. To define the direction of induced current, you would use the right hand rule of Fleming. You get the point? Which means remember that I induced, I right. So if you find two, if you study induction, you will use right hand rule. If you find magnetic force, you will use left hand rule. If you get the point, please write one. تمام، يعني هنعمل ايه؟ نفس الرول بس على الرايت هاند. The same rule. Okay, Fleming's right hand rule: hold right hand thumb, first finger and second finger at right angles one to another, such that the thumb points to the direction of the force or the motion, the first finger the field, then the second finger will induce the current. Okay, and inshallah Rabbil Alameen, we will solve on it and we will find it easy because alhamdulillah Rabbil Alameen, we made good practice level on the left hand rule, and the right hand rule will be the same. But the point here is to decide which situation you are choosing. Okay, again, if the situation is a current carrying wire, okay, placed in a magnetic field, يعني the wire is already passing in the magnetic field, okay, we would use the left hand side. If the situation is induction, يعني there is no source, the current will be produced because of the motion, okay, so this is right hand rule. That's it. And we will solve again, inshallah, on it. In case of solenoid, we would use also the right-handed grip rule as we explained before, and inshallah, I mean, I'll show you again this point, but with a very important idea which is called lens rule. Okay, lens rule. So again, I have to show a very important point here, which is lens rule. Please write this point after me. And I'll send it again after the period. Look, طبعا the name of lens rule is not with us. The name lens rule is not, yani we don't have to know it's called lens rule. Okay, but you will not lose anything to know its lens rule or law. Lens rule or law says that induced electromotive force and current happens such that it opposes. This is a very essential point, by the way. But when I transfer the file to GoodNotes, sometimes some pages, there is some error happen, okay? And some pages may be skipped, okay? So please write this after me, and I'll send the page to you, inshallah, by mail later from the original file, okay? So Lenz's rule, induced electromotive force and the current happens such that it opposes the change that causes them. This is the Lenz rule. Yani, what does it mean? Yani, for example, imagine that we have a coil like this. And we bring N pole of a magnet close to the magnetic field line. Close to the coil. What will happen? The current, the induced current, passes such that it forms in end opposite to N pole to repel it, يعني to oppose the change. ركزوا معايا في الكلام دوت. What does it mean? يعني here this is the coil. There is no current now. Suddenly it finds the magnetic field of N coming towards it. So this is the change that will cause electromagnetic induction. The coil will make current pass such that it blocks this change. يعني هو it finds N coming towards it. So will it need to block the N or يعني welcome the N pole? I'm waiting for your answers.
تاني كده ايه ولا ايه؟ هتبوش ولا ايه؟
يعني will it need to repel يعني will the coil here need to repel the incoming the coming in or to repel it or to welcome it and attract it. شكرا مصطفى. أنس. لا احنا قلنا that change happens such that it opposes يعني عايز it wants to decrease the change. تمام يعني there was no n here, suddenly n comes, so he wants to what to do, it wants to do what يا أنس؟ ها شكرا يحيى. To repel it, it wants to block it. Okay, so the current passes here such that it makes this face N and this face S. So the current passes, for example, in this direction مثلا. طيب if N goes away like this, now N is moving away. So the coil wants to do what? Wants to do the opposite. يعني wants to attract it or to repel it? Huh? Excellent, Anas. Excellent يحيى. ها مصطفى. بالظبط. wants to attract it. تعال رايح فين؟ Okay. So the current here or the induced current here passes such that it forms ايه بقى؟ هيعمل ايه هنا عند السايد دوت؟ ان ولا اس؟ بالظبط. احسنتم. Thank you everyone. It forms S pole at the end opposite to the moving away in pole to oppose the change. Okay, well, please write this in your notes, in your copies of your notes, right after me. Take screenshot for now. Okay. طيب, let's have. طيب, Mr. If I want to know, so this will be S and this will be N. Mr. If I want to know where is the direction of the current, طبعا هنا the direction of the deflection will be in this direction. لكن if I want to know where is the direction of the current, how? Using a right hand rule, grip rule, مش Fleming rule. يعني right hand grip rule, because I'll make my thumb towards the N, so the curling fingers will show me the direction of the current. If you get this point, please write 7. تاني يعني I'll make my right hand thumb toward the N. Then the curling fingers will show me the direction of the current in the coil. As we explained when we talk about the right hand grip rule for a spring, for a coil أو solenoid. تمام. يحيى only يحيى wrote 7. تمام أنس. ها مصطفى.
ينفع تعيد؟ سرحت انا في الحته الاخيره دي.
ينفع قوي، مفيش أي مشكلة. بص يا مصطفى، دلوقتي خلاص احنا عرفنا ان مين هيبقى ان ومين هيبقى اس، صح ولا لا؟
عرفت.
جميل. انا بقى عايز اعرف الدايركشن بتاع الكرنت هيمشي ازاي. تمام.
هستخدم الفليمنج.
ايوه، لا مش الفليمنج بقى،
لا،
الفليمنج
الرايت هاند
بستخدمها.
جريب.
ايوه هستخدم الجريب رول بالظبط، هحط الثumb ناحيه النورث. تمام، يبقى الكيرلينج فينجرز هتوريني الدايركشن بتاع الكرنت. تمام. تمام. طيب هناخد تو سيتويشنز التانيين اللي هم 3 مثلا. لو انا عندي هو خلاص بقى كله زي بعضه، لكن for example this is S, this is S and this is the solenoid. The S is moving in this direction. Huh. So the current will move such what which magnetic pole here. Hmm. Yes, excellent.
ان.
S. And here N. Okay. The fourth situation, S is moving away. So it will make N here and S here. These 4 situations are very important, by the way. You have to write them because again the page was dropped when I changing the file from PDF to this the formula. يعني to when I imported the file from PDF to the application that I put. I didn't find it now. It's a strange thing. Okay. طيب. عموما I resend it to you إن شاء الله رب العالمين. Okay. Well, so here this is the right-handed ripple of coil as we expect. Well, now إن شاء الله رب العالمين. Okay, this is the electromagnetic induction as we explained it, and I'll stop this video here and I record the applications inshallah in a new video inshallah رب العالمين now.